we will continue our discussion on IC engine. So, today we will discuss about combustion in CI engine. We have discussed up different aspects of the spark ignition engine combustion. We have discussed about abnormal and normal combustion. Normal combustion is very hard to achieve, but we get always abnormal combustion, and there are two different subparts we have discussed, that pre-ignition or surface ignition, and also an important is that detonation and knocking, that is also the part of the combustion process. So, we have understood that in a spark ignition engine, combustion is initiated the charge, compressed charge, which is close to the spark plug, from there combustion is initiated, and there we can see a flame. So, as I said you that the combustion, whether it is in SI engine or CI engine, combustion, the normal manifestation of the combustion is very important. Normal manifestation of combustion is essentially the appearance of visible flame in the visible flame either seen in the open eye in the combustion chamber. So, this is the important, that when you can say that combustion is started, that means it will manifest itself by the appearance of visible flame in the combustion chamber. Now, that we have seen that in a spark ignition engine, spark plug is there which ignites the fuel air mixture or the charge which is close to that spark plug surface, and then suppose if I have a spark plug here, and from here the combustion will start from here. That means we can see a visible flame over here when spark plug switch is on. Now, we can say that combustion in a SI engine is rather almost uniform, in a sense that whenever flame is produced or flaming is developed in the region very close to the spark plug, then we will have again a huge amount of heat generation, and that heat will be utilized, that heat will try to utilized, or rather to increase the temperature of the compressed charge which is there nearer to that flame, and in that way. So, whenever this flame is developed here, because of this huge combustion is essentially a chemical reaction, exothermic chemical reaction. So, we will have huge heat generation, that heat will try to raise the temperature of the compressed charge which is there close to that flame, and the nearby compressed charge again will ignite, and again combustion will be there. So, in that way the flame will proceeds in the combustion chamber, and overall the entire compressed charge in the combustion chamber will take part in the combustion, and combustion will be completed. So, here the combustion is almost uniform, but we have seen that not only uniform, that if it is uniform, rather when the flame moves in a fairly uniform manner, then we can say that it is normal combustion, but it is not the case always. We have seen that there are cases when we have pre-ignition, and of course surface pre-ignition leads to the phenomenon of detonation or knocking. Now, we have identified that by somehow there are spots in the combustion chamber where temperature is higher because of the continuous heat generation, and temperature will go high in such a way that that whenever compressed charge is coming in contact with those surfaces, those surfaces will act like a artificial spark plug, and we may get a secondary flames from there. Now, whenever secondary flames is being produced, that flame again will try to move, and if we have discussed that the preparation phase, or the that we have discussed today, that whenever we are having critical pressure, that whenever that main flame front is traveling, it is acting like a piston, and it is also creating pressure on the furthest charge, and whenever the pressure at the furthest charge will reach at the critical pressure, and then we require a finite time, that is known as, that is similar to the preparation phase. So then even the temperature, we have seen that temperature, if the temperature becomes so high, then it will automatically try to ignite the charge which is there. Otherwise, even the temperature is not so high, because of the pressure that is being produced because of the movement of the main flame, the furthest charge will overcome the preparation phase time and it will ignite. So we have seen that if we somehow can restrict the movement of the flame front, main flame front, so that either not restrict, if we can restrict the movement of the secondary flames, or we can increase the speed of the primary flame or main flame, then we can somehow avoid or prevent detonation or knocking. So I mean, we can say that the time by which the main flame will be reaching at the furthest location, and by that time the although the temperature will be higher of the surface at some locations, but the charge which is there won't be able to, I mean the preparation phase or the secondary flame although being developed, but it won't be able to proceed. So we need to ensure that the speed of the main flame will increase, so that the secondary flame, even though secondary flame won't be produced, it is reservable, or even though they are produced, they won't be able to proceed, so that direct collision which eventually leads to violent vibration with audible noise, that is known as detonation or knocking, won't be there. So we have seen that if I can increase the speed of the main flame front, so speed of the main flame is very important for the very important, I mean this is important for the prevention of detonation. And we have discussed a few things, that how we can, that there are many ways to control the detonation. So speed is the speed is one of them. Otherwise we may have continuous supply of coolant, but we need to ensure that maybe we can supply coolant to reduce the temperature of those spots which are acting like artificial spark plug, but at the same time we need to ensure that the temperature won't go beyond a certain value, otherwise again combustion efficiency will be reduced. So only one important aspect is if we can increase the speed of the main flame, so that even the secondary flames are being produced, they won't be able to collide with the main flame. So now what are the factors or affecting the main speed? So we have understood up to till now we have understood that the speed of the main flame is very important, that is crucial for the prevention of the detonation. Now we need to know what are the factors. So factors affecting the main flame. What are the factors? So first one is, of course we have discussed, that is known as air fuel ratio. So we will discuss in one by one air fuel ratio. Second is, of course, is very important, that known as pressure, inlet pressure, precisely inlet pressure, and third is turbulence. So we will discuss one by one. So how these three factors, I mean influences, how these three factors influence the flame speed in a combustion chamber, so that we can control or prevent the detonation. So we will discuss first that which is known as air fuel ratio. We have discussed on last class that air fuel ratio, that is air fuel ratio, it influences the flame speed through the, by how. So we have seen that the higher, or rather if the air fuel ratio is higher, because we can't supply always higher air fuel ratio, because higher air fuel ratio will eventually will not be economic always, because we have discussed that always we need to supply a stoichiometric air fuel ratio, that is chemically correct air fuel ratio. But okay, fine, that to prevent the detonation, if we need to increase the main flame speed, we can reach the flame air fuel ratio, but it should be again it should be economic again. So we can say that if the air fuel ratio is higher, I mean it is higher than chemically correct, slightly somewhat richer than chemically correct, higher, or I can say that, or somewhat richer than chemically correct, that is stoichiometry, chemically correct ratio, the flame speed will increase, flame speed will increase. So, this is quite obvious because if it is richer, that means we are having efficient combustion. So, we will have huge heat generation and high pressure. So, that may increase the main flame speed, and we need to know that it should not be very high than the from the chemically correct ratio, but it should be somewhat richer than chemically correct ratio, so that it will increase the air flame speed. Number 2, that is we have discussed about that is inlet pressure. Inlet pressure. So, what effect does it have on the propagation of main flame, rather how it controls the speed of the main flame. So, we can say that generally increased pressure increases the rate of chemical reaction. We know that if we increase, so increased pressure generally increases the rate of chemical reaction. So, that is what I have discussed just now, that if we increase somewhat richer air fuel ratio, that means we need to ensure that the chemical combustion will be more efficient. That means rate of chemical reaction should be high, and which in turn will try to increase the flame speed. Similarly, if we increase the inlet pressure, that is increased pressure generally increases the rate of chemical reaction, and thus it is not surprising to find that increased pressure increases the flame speed in most kind of experiments. So, therefore, but thus it is not surprised, to find that the increased pressure, that the increasing pressure will increase flame speed in most kinds of experiments. Actually, the higher inlet pressure and temperature as well increases flame speed because the higher inlet pressure helps to better homogeneous mixture of helps to better homogeneous mixture of vapor and air, I mean mixture of charge rather, and increases the flame to increase the flame speed. So, that means if we reduce how I can increase the throttling, how can increase inlet pressure, that is by if we have throttling, then we can throttling reduces the inlet pressure. So, we should have full throttling or nearly full throttling, so that we can increase the inlet pressure, which will help to have a homogeneous mixture of the charge, essentially to increase the flame speed through efficient or through the higher rate of chemical reaction. And next we will discuss, which is important again, this turbulence. So, it is again we can't expect that how turbulence will help to have a better or higher flame speed. So, the turbulence, right. So, what is turbulence? See that if we increase the speed of the piston, so that means speed of the piston if you increase, so then we can increase the flow of whenever we are compressing, of course we can increase the speed of the piston, will increase the Reynolds number of the Reynolds number. That means the compressed charge, the charge which is being compressed will have higher Reynolds number, and then we may have better flame speed, and by how, that is what I will discuss now. Now question is, the turbulence is essentially whenever we are telling that in fact the flame speed is greatly affected by the turbulence. I can write that flame speed is greatly affected by the turbulence. So, now by how we will write turbulence means, I mean again I am telling that we can say turbulence, that means there are vortices. So, turbulence means formation of vortices, which was, I mean again I am telling it is as I said you that this course required knowledge, basic knowledge in fluid mechanics. So, I am telling turbulence, if we increase the speed of the piston, perhaps the charge which is being compressed will have higher Reynolds number, and because of higher speed, and since density and viscosity are same. So, turbulence means the existence of vortices, a chaotic movement, erratic movement, rather existence of vortices. So, existence rather vortices or formation of vortices, I can say formation of vortices. So, now if I draw, suppose this is the main flame speed, and if we have vortices, so we will have, if we have a vortices very on the top surface, then what will happen, the flame which will come, there will be change in momentum, I can say, and then we will have rather instead of uniform movement of the flame, we will have a movement like this. So, these two are vortices. I have taken two example. Let us say this is surface A and this is surface B. So, I am taking example case 1. So, whenever turbulence is there, that means there are vortices. So, whenever vortices are there, and whenever we are having vortices in front of the main flame, then there is, suppose if I have taken 2 points A and B. Now, question is if the size of the so case 1, when size of the vortices is size of the vortices are small, is small, and I can take another example. This is case 2, size of the vortices is large. So, that means I can take a big vortices again I am taking two different points A and B. So, let me discuss. So, these are vortex we have seen. So, whenever we have turbulence, so we assume that we are assuming, but it is true that there are vortices or vortex formation is there. So, vortex will try to disturb the main flame by how, that is what it is shown in figure case 1 and case 2 through a zigzag line. So, whenever the vortex is having always either clockwise or counterclockwise movement. So, we can see at point A when flame is there, because vortex will deform the flame speed by how, at point A momentum will transform from outside to inner side. That means, when vortex is from the main flame which is being developed, it will be disturbed because of the presence of vortex or vortices. At point A, if we consider both the cases, case 1 and case 2, at point A momentum will go because of this, we have considered the counterclockwise rotation of the vortex. So, at point A the momentum will transform from outward to inward. That means the vortex will try to take the flame in the inner side. Similarly, at point B again momentum will transform from inward, inside to outside, and then it will try to stress the flame. The vortex will try to stress the flame, and as a result of which you will get this zigzag motion. Now question is, eventually if I now plot, so actual mean speed was like this, but now eventually as if we will get the flame speed like this. So this is now the flame speed because of the vortex formation. That means flame will be stretched, or apparently we will have a higher velocity because of the vortex formation. Now we need to ensure that whenever vortex size is small, there is no problem. We can get even flame which is a continuous flame, and but the apparent location or the speed of the flame will be increased. Note that when we will have relatively larger vortex, then of course the same phenomenon will be there. That means momentum will transform from outward to inward at point A, and again it will be from inward to outerward at point B. And since the vortex size is large, so higher momentum will be transformed from inward to outward, and again outward to inward, and again from inward to outward. And there might be a situation when and it is too large, that the momentum transfer is too high because of the higher size of the vortex. So vortex formation, I can say in this context, whenever vortex or vortices are formed, they are taking energy or they are extracting energy from the mean flow, and higher vortex are having higher energy. So that means when momentum is getting transferred at point A from outward to inward, because of the relatively larger size of the vortex, there will be a larger momentum, and larger momentum will be transferred from outward to inward at point A, and similarly from again inward to outward at point B. Momentum will be too large that this large vortex sometimes may leads to the rather it won't allow to have a continuous flame, rather it will try to extinguish the flame. So because of the stretching, so here we may get, of course we may get relatively higher velocity again. So we may get here, so this is the flame speed, apparent flame speed. So this is the flame speed. So if we have a larger vortex size, then we may get even a larger velocity flame speed, but we need to keep in mind that sometimes because of the larger transfer of momentum, the larger vortex may extinguish the flame. So this larger or higher momentum transfer from inward to outward at point B may extinguish the flame. So our objective was to have a higher flame velocity, or instead of getting, we may get higher flame velocity, that is true, but we may get the chances are there that the flame might extinguish. So flame might extinguish. So I mean it is not our objective at all. So we have discussed about the combustion, different aspects of combustion in SI engine, and we have discussed that if we can control the normal combustion is there, but normal combustion is very hard to achieve. So always there are abnormal combustion, that is surface ignition and detonation, but detonation is not a desirable phenomenon at all. So we need to ensure that we always prevent detonation. So by how we can control the detonation, prevent detonation by controlling the speed of the main flame, and we have discussed about there are three important factors, that is inlet pressure, air fuel ratio, and the turbulence, and we have discussed their effect separately. So now I will discuss about the combustion in SI engine. So we have seen that combustion in SI engine very important, that combustion in CI engine is not combustion in CI engine. Combustion in CI engine is not similar. There are I mean to be there are differences. I mean if we compare combustion of CI and SI engine. So if we can recall, rather if we try to recall that in a CI engine we do not have spark plug. So what is done basically, the intake air during intake stroke is getting compressed during compression stroke, and towards the end of the compression stroke temperature and pressure of the air becomes higher, of course, because CI engines are having preferably higher compression ratio, always CI engines are having always higher compression ratio. So, so that means pressure and temperature will be higher at the end of the compression, and pressure and temperature is higher in, so that whenever we start injecting fuel through fuel injector or nozzle, then it will try to the higher pressure and temperature of the air allowed to ignite fuel automatically without help of any external agent like spark plug. Now, this is true that, so this combustion CI engine is not the fact that we have spark plug, so we can have a visible flame from the region very close to the spark plug, and that then that flame front will proceed towards the next region of the compressed charge, and there again combustion will take part, and again there will be release of heat. That heat will try to rise the temperature of the surrounding layer, and in that way entire combustion will be completed. So, rather this the combustion in a SI engine relatively is happening in a rather controlled manner, but in case of a CI engine it is not happening in a controlled manner. Rather we have high pressure, high temperature of the air, and we are injecting fuel. So, depending upon the spray pattern of the fuel and depending upon the finer size of the fuel droplet, overall combustion will be dictated. Rather, I can say that overall combustion will be completed. So, now there are 3 different phases of combustion. So, 3 different phases of combustion in CI engine, 3 different phases of combustion. Number 1 is number 2 and number 3. Number 1 is essentially number 2 and number 3. Number 1 is delay period, that we will discuss, delay period. Number 2 is a period of rapid combustion, period of rapid combustion, and number 3 is third phase of combustion, which may or may not be present, third phase of combustion. So, this phase may or may not be present, may or may not be present. So, we will discuss again what is delay period, period of rapid combustion, third phase of combustion, but let me tell you the chemical reaction during combustion. So, I am writing while a chemical reaction during combustion, because we are using fuel, is a family of hydrocarbon, it depends, and we have discussed that which fuel is used for which engines. I mean, essentially it is a hydrocarbon. So, while a chemical reaction during combustion are chemical while chemical reaction during the chemical reactions during combustions are undoubtedly similar, very similar in SI and CI engines. The physical aspects of two combustion processes are quite different. So, this is very important that chemical reactions are undoubtedly similar, because we need to supply air, there will be hydrocarbon, fuel is hydrocarbon. So, in presence of air it will ignite and it will give rise to vapor and carbon dioxide, and it will release heat. So, they are similar, but the physical aspects of two combustions are different. What are the difference? So, we have understood, rather we have learned we have the process of combustion in a SI engine. Why? So, what are the processes in a SI engine? In a SI engine, during combustion, rather during normal operation, I can say during normal operation, at the time of ignition, of the fuel is substantially falls in gaseous state and fuel air are rather fuel air or residue are uniformly mixed. That is true, because the fuel which is used in a SI engines are almost fall in the at the time of ignition gaseous state, and if we use carburetor, of course the function of carburetor that I have discussed, that it allows to have a homogeneous mixture of air fuel ratio. So that means fuel and air are uniformly mixed, and ignition occur at one point, and at a ignition occur, that is very important, ignition occur at one point, that is we are having external spark plug and there ignition start, right, and this is very important. But in case of a CI engine, and we have discussed that ignition occurs at a given point, flame combustion initiated, that means we can have a visible flame, and when that flame is produced, that flame and that reaction is basically exothermic, we get huge heat. That heat is used to raise the heat raises the temperature of the surrounding charge, and there again charge will ignite, and again we can see visible flame, and in that way overall combustion is completed. That is it is almost occurring in a uniform manner. Of course, we have discussed that this is not always possible to have uniform or rather normal combustion because of the hot spots. So, but probability is there that there might, if we have a better control, that if we can control the temperature of the hot spot, we can have a better rather uniform combustion. But in a CI engine, in a CI engine, air is diluted small fraction of a residual gas. So, we take air, so air is diluted, diluted by small fraction of residual gas. That means in a CI engine, we take air during intake stroke, we compressed air, then we spray fuel. So, that air, although air fuel mixture is again diluted in SI engine as well, but in a CI engine air is diluted by small fraction of residual gas, and liquid fuel is sprayed into the cylinder during the end of the compression stroke. So, this is the case, that is what we have discussed many a times. Now, question is, pressure and temperature of the air, or rather pressure and temperature of the air in the cylinder contents are both very high. So, we are utilizing that condition. So, pressure and temperature of air in the cylinder at the time of fuel injection, are very high. Some chemical reaction undoubtedly begin high. Some chemical reaction undoubtedly begin as soon as the first droplets is injected into the cylinder. As soon as the first droplet injected into the cylinder. So, what is the case? So, since the pressure and we are utilizing the high pressure and temperature of the air itself to self ignite the fuel. So, since the pressure and temperature of the air is so high, the moment at which the first droplet enters into the cylinder, that will take part in the combustion. So, I mean chemical reaction. This chemical reaction starts so slowly that our usual again writing. However, this chemical reaction starts so slowly that the usual manifestations of the combustion, that the usual of combustion, that is appearance of visible flame, appearance of visible flame occur only after appreciable time, occurs only after an appreciable time, which is called delay period, So, although the moment when first droplet is sprayed into the cylinder, combustion will start because the temperature and pressure is very high, but the rate of chemical reaction is so slow that the total usual manifestation of the combustion, that is appearance of the visible flame, occurs after a finite time interval. There are many reasons I will discuss, because I have already discussed that what do you have in physical delay, that is a total delay period, chemical delay and physical delay, and we require a finite time interval to have this physical appearance of the flame. So, that means this delay period constitute two different times, one is known as physical delay, another is chemical delay. Chemical delay is directly associated with the chemical composition of the fuel, and physical delay the time required for the droplet evaporation, and we have discussed that we are relying on the mechanical component like nozzle and all those things. So, after keep on functioning they will after keep on using they will start malfunctioning. So, it is not expected that nozzle will perform in a similar way when it was during the initial stage. So, all these factors we need to take into account, we need to consider rather, because if we do not consider those factors, then we cannot the entire combustion cannot be described. So, so these two delays, I mean chemical delay and physical delay, constitute the physical total delay period, and this is the delay period. Another aspect I am telling, so this is the delay period, and so the first phase of the combustion is the first phase of the combustion is basically the delay period, that is what I am telling. So, it requires finite time interval, and again I have discussed that in a diesel engine time and space where ignition occurs is not fixed, and but in case of SI engine we have seen that it starts from the spark plug area. So, since it is not fixed, it cannot be controlled as an ignition sparks in case of SI engine. So, that means in a diesel engine time and space where ignition occurs is not fixed by anything, so easily controlled as an ignition sparks occurs in a SI engine, because SI engine it is fixed that spark will occur from the region very close to the spark plug. Flame normally appears while the distribution of fuel in the air and residual gas mixture is extremely non-uniform, while a considerable part of the fuel is still in the liquid form, because whenever you are supplying fuel through fuel nozzle into a cylinder, the part of the fuel is remaining still in the liquid form. So, because of the liquid inertia, it is not always possible that it is not in a gaseous state, and this is the disadvantage. And because of this high compression ratio, the gases in the cylinder at the time of injection are well above the temperature and pressure required to support chain reaction in a uniform fuel mixture. So, what the point that I would like to emphasize is that the combustion in a CI engine is a question of local condition, because it depends upon the local composition, local state of the pressure and local pressure and temperature of the charge in the cylinder. So, we can't say that it is not a homogeneous mixture of air and fuel, that is the case when we discussed in the context of SI engine, but in case of a CI engine it depends upon, it is a question of local state of the local condition of each part of the charge, and is not dependent, and it is not dependent and although it may be by that, but we can say that whenever you are having first phase of combustion, that is a delay period, then the flame will try to propagate, but it is not possible that we can have a fairly uniform speed of the flame. It always depends upon the local state of the charge, that is the pressure and temperature of the charge. Since it is I mean, although we are having higher pressure and temperature during the compression stroke, but since the liquid is still there are certain amount of fuel is still remaining in the liquid form, so it is not always possible to create chain reaction immediately. I mean, the case like what we had in case of SI engine. So this is the delay period we have discussed. Next is we will discuss about the period of rapid combustion. So period of rapid combustion. So if we period of rapid combustion, that means very important that combustion in this phase is due to chiefly burning of such fuel. So I am writing, so we need to give some time so that the charge at each and every points in the combustion chamber will go above that preparation phase. Although the pressure and temperature is so high, but since certain amount of fuel is still remaining in the liquid form, we need to give certain amount of time to complete the chain reaction, and after that time is over, then entire charge will take part in the combustion. Since it is a local function or local, it depends upon the local condition of pressure and temperature of the charge. So combustion in this phase is very important. Combustion in this phase is mainly due to the burning of such fuel as had time to be evaporated and mixed with air during delay period. So during delay period, we have delay period with that delay period constitutes physical delay and chemical delay. So the fuel is the burning of fuel, such fuel which had time to be evaporated and mixed with air during delay period. The rate and extent of burning during this period are closely associated to the length of the delay period and related to injection process, are closely associated with the length of the delay period. So until and unless the entire charge goes over that that means over that delay period we cannot have the complete rapid combustion. That means we have seen that the moment when we first spray fuel drop, that fuel drop may take part in combustion because of the high pressure and temperature of the air, but the rate of reaction is so slow because of we cannot have a very homogeneous mixture of the air fuel. Also the fuel is not largely in the gaseous state. So and because of that, reaction is so slow that we require certain amount of finite time to complete the combustion of the entire charge which is there in the that is there in the cylinder. Now the rate and extent of burning, that is combustion of the rapid combustion, means the combustion in this phase is mainly due to the burning of such fuel which had time to evaporated and mixed completely with air during the delay period, and the rate and extent of burning during this period are closely associated with the length of the delay period and its relation to the injection phase, and associated to the length of delay period and its relation to the injection process and the injection process. And third phase of combustion, which may or may not present, third phase of combustion. The third phase of combustion, this phase of combustion is the period from maximum pressure to the point where combustion is measurably completed. Measurably complete. That means maximum pressure rise we had, so we can say that we can ensure that we can say that the combustion will be completed. So, maximum pressure is there, but from that time to the point when combustion is measurably complete is known as the third period of combustion. So, delay period, period of rapid combustion and third phase of combustions are the total or overall combustion of the CI engine. And we have discussed, though chemical reactions are similar in both the engines, SI and CI engines, but there are certain physical issues which make the combustion processes to be different in both the SI and CI engines. So, with this I stop my discussion today and we will continue our discussion in the next class. Thank you.